Hello everyone, my name is Amjad Ullah. I'm a research associate in the research group called Center for Parallel Computing, in short form it's called CPC, which is part of the University of Westminster. Today I will be discussing about a software tool called MiCADO, which we have developed in CPC, and its purpose is to dynamically manage the Docker containers in multi-cloud and edge environment. So in this talk, I will mainly talk about MiCADO, this system in itself. In short, it is an application level cloud orchestration solution. It is the outcome of a previously European project called COLA. It is available as an open source solutions, as a community versions, as well as a managed service. Further in this talk, I will also talk about two extensions of MiCADO. One is called JQuery, which is in order to support the execution of container-based batch applications in the cloud environment. And the other extension is called MiCADO Edge, which is the edge extensions which demonstrate that how we are going to orchestrate applications in the extended cloud to edge ecosystem. So in order to understand the overall context of what MiCADO is and what MiCADO does in terms of the functionalities, let's try to simulate it through using a kind of story or as in a scenario. So imagine in this scenario, there is a developers or an owner of an applications. Now, this developer has an application, a microservice based applications. So, which consist of a set of different microservices. Now, this microservices, each microservice runs in a separate Docker containers, and these Docker containers are placed either they can be available in Docker Hub or they can be available in some Docker repository. Now, now the core purpose for this application developer is to deploy and manage this application in the cloud environment. Now, in order to do that, there are a number of cloud environments. So the application developer has to choose one of the cloud environments in which he would like to deploy and execute these applications. So let's say there is a different choices of cloud environments, for example, AWS, Azure, Google Cloud, and others cloud as well. So this application developers now has to choose one of the cloud environment where he would like to deploy these applications. And once the cloud environment has been selected, then there are in each cloud environment there are various kind of computational resources offering like a different different kinds of virtual machines, and they have to also choose what kind of virtual machines they would like to use for their services to run in their specific cloud environment. So let's say there are this application developer has to choose these options. But now once the application developers are happy with the setup resources they would like to use for the application for their applications, then what they need to do is they have to kind of specify that which service of their application has to run at which virtual machines in the selected cloud environment. And once this has the application developer choose this, then they will deploy their services on those respective virtual machines which have been chosen. So, but now does this mean this is it? No. In addition to that, now these application developers were required to attach various kind of policies which will govern the runtime execution of this application. The policy examples could be that what kind of monitoring the application developers would like to be interested to perform, what kind of scaling policies they would like to associate so that the dynamic reconfigurations of the applications can be performed at runtime, and also the security aspects of the applications, what kind of application level security settings they would like to be implied on these applications. So now the developer has to provide a set of custom policies in relation to these three categories. Now, Okay, so these are the things which in application developers are required so that they can run and execute their applications in the cloud environment. Now there are so many different steps which the application developer has to go through in order to finally deploy their applications to the cloud environment. Now, okay, in respect to these steps, MiCADO systems facilitate the application developers exactly in order to do this step. So MiCADO help them to do this step in a cloud agnostic and customizable way, so that they can able to orchestrate their applications in the cloud environment. Now, how this happen is that on this slide, on the previous slide, we mentioned that there are these number of various things which the application developer has to give as an input to the system. For example, the resource specifications, the service, what services or what containers there are belonging to the applications, and then the mapping from services to the resources, and the descriptions for the various policies which they would like to imply on their applications. So let's say the application developers put all these details into a description file, and within the MiCADO system, we call it ADT, which means application description template file. And this application description template file is based on a standardized modeling language called Tosca. So the application developer has to write this description in the Tosca format. And this Tosca is basically a modeling language to describe the topology of cloud-based services, and not only services, but their all components and their relationship with each other, and with the other entities of the system, and also with the processes, which is in this case it would mean the various policies which would manage these services at runtime. So once the application developers prepare this template, then they have to provide this as an input to MiCADO system, which on this slide appear as this component called MiCADO master. So MiCADO master is the main component of MiCADO, which run on a separate virtual machines. In this case, these bugs represent a virtual machine. And MiCADO master will translate this template file and then do the necessary functions which is required and described as per the template. In this case, what will happen is that MiCADO master will dynamically create the required setup resources, the required setup virtual machines, and then deploy the respective services which was described in service to resource mapping in the template accordingly. And once this deployment process is successful, then MiCADO will then start as per the defined scaling and reconfigurations policy. It will manage the execution of the application as per those defined policies. Now, on the previous slide, I mentioned about this MiCADO master and MiCADO worker nodes. Now, these components were running on virtual machines. So the MiCADO masters were running on a separate virtual machines, where MiCADO workers had some components which will be running on each worker adjacent to the services running on the worker nodes. Now, on this slide, we will look into what are in these boxes, what are in these components, like what are the internal details. So MiCADO system is not developed from the very scratch. It also consists of various built-in open source tools which are like developed for specific purposes, and we include it into this MiCADO system. We integrate it in this MiCADO system. So MiCADO system is actually based on the integration of some already developed tools, and some of the components were specifically designed and developed for this MiCADO system. So this slide particularly distribute into three parts. So the very left part the application description template. That's the description template which we talked about on the previous slide, which will consist of all the required descriptions provided by the application developers in relationship to the various resources and the policies and the services descriptions, and it's based on Tosca format. Now the big box, which is the MiCADO master node. Now MiCADO master, so there is like these various components which are being presented in 2 rows. So let's first focus on the bottom row. So in the bottom row, there are 3 components mainly. One is called cloud orchestrators, the second is container orchestrator, and the third is called monitoring systems. Now so MiCADO utilize these already developed components. The first one is the cloud resource orchestrator, through which MiCADO dynamically create the virtual machines. So now, so far, we integrated 2 different cloud resource orchestrator. One is called Octopus, and the other is a well-known cloud orchestrator tool called Terraform. And the reason for including these 2 different, because this Octopus has support for some cloud providers for which Terraform does not provide support. So that's why it was included, so that MiCADO support a large range of cloud providers. And then on the container orchestrators, we had initially developed, integrated the Swarm as a container orchestration tools, and then later on we replaced it with Kubernetes. So now we have support for both container orchestration systems. And this is that once the resources are created, then we perform the container, manage the container orchestrations using the functionalities provided by these tools. And for monitorings, we have these Prometheus tools, widely used monitoring tools, which is there in order to manage and extract the monitoring informations from the various worker nodes. And using these monitoring informations, we then manage to perform the scaling by using the various matrices, retrieve the various matrix information is retrieved from the worker nodes. Now on the top row, we had these 3 components which were specifically designed and developed for MiCADO systems. The first one is called submitter. So the whole purpose of the submitter component is to receive the Tosca template and then translate the Tosca template into specific low-level MiCADO specific details so that it can be transformed to the respective component, so that they can perform the things which they were developed for. And then we have this dedicated policy keeper component. The purpose of this is to enforce the scaling policy. So the scaling policies descriptions provided by the users in the template will then, and runtime will be managed and executed by the policy keeper component. And then the last one is the optimizer component. The optimizer component is the purpose of the optimizer component is it is based on machine learning algorithm, and it perform optimization. So the users can include the output, like take a recommendations from this optimizers component in relation to the various to perform the various kind of scaling. Now on the worker side, what we have is that on here on the bottom box, we have the service, which is like a Docker containers, which would be the application service running on a particular worker node. But in addition to that, we have this node exporter component and CA advisor. These are monitoring agents, and these are the agents which help us collect the matrices, the required metrics from this worker node, which will then be pushed into the Prometheus server on MiCADO masters, and which will then be utilized by the policy keepers in order to perform the scaling. Okay, so now let's look into a bit deeper that what are these templates, how the application developer will provide these specifications to the various things. So earlier in the earlier we specified that through this application description, the application owner will provide the resources related information as well as the service related information, the policies as well. So on this slide, the first this part represent the corresponding Tosca code to define a worker, a virtual machine. So if you see, we in MiCADO ADT we provided these specific types for different supported cloud. For example, in this case, it says Cloud Sigma, which is one European cloud providers which we support which is supported by MiCADO. So this means the definitions for a worker node in Cloud Sigma cloud. And in addition to that, for this worker node, the users will be able to provide the informations like in terms of the instance, what a specific instance in that cloud, the SSH keys goes to that is required for that virtual machines, the ports and the image, and all those details will be provided here with respect to the specific cloud. Now, in the second part, we have this service definitions. For example, in this case, StressNG would becomes the name of this server, this service, and then we can provide like the container image, the arguments which are required by their specific containers, and the various resource specifications, for example, in terms of their CPU and memory required for that to be consumed by that containers. So all these, the container related informations will go into the service definitions like this, and it can also include all the related configurations and the volumes which are required for the containers. Now, further to that, we can also, and the most important interesting aspect is that the users will be able to provide details for the policies, for the scaling policy, the custom scaling policy. So this empower the application developers to come up with their own highly customizable scaling policies. So users in this case can specify that whether they would like to perform the monitoring with which particular service on which particular worker node, and all such details can be specified explicitly. And then MiCADO support both kind of scaling, not on both kind of scaling. That is, it means that for container as well as for virtual machine separately. So in this case, the application developer will explicitly say that whether a scaling policy which they are defining could be implied on a service. For example, in this case, the target is a service, where, for example, in this case, a target could be a virtual machine and a worker node. So they can provide a specific different policies for different service as well as different policies for different VM. So there is the provisions to apply multiple policies. This slide then further provide an example that, okay, how we are going to provide these policies. So for example, in this case, what we have is that on this side we have the virtual machine policies, and on this side we have the container-based policies. In this policy, for example, in either one, let's focus on this one. In this one, what we had that a users can, based on the monitoring metrics coming from the Prometheus, they can define their alerts, and based on their alerts, then here in the scaling rules, they can use Python programming on their own in order to define whatever kind of policies they required for their application. So from MiCADO system, we provided various parameters which they can access, and they will be able to change it through this scaling logic. For example, in the virtual machine case, at any point in time, they can dynamically configure how many virtual machines they will need. On the container side, it would be with respect to the services, like how many service instances they will need at any point in time. And then they can, based on their own specific logic, they can provide these scaling policies. Now, it's not only limited to the scaling policies, but if they have any kind of security policies in relation to their application, for example, application level firewalls, they would like to block some IPs, or they would only want to allow the traffic from certain specific IPs, or how they would like to kind of disseminate some secret across the different application components. They can also dynamically provide that through the application description template. In this particular case, for example, for this specific service, Nginx app, they can, for example, they can provide the certificate and the target ports which should be applied on this particular service. So this way, they don't need to change anything in their applications. They just configure and provided these descriptions in these application description, and they will be able to the MiCADO will take care of implementing these policies for the specific application. Now, how this works, like how the from MiCADO side, when the MiCADO receive in a Tosca ADT, how it interpret and how it pass information to the other components. So earlier I mentioned that there is an application submitter component, it receive an ADT, and then for the resource specification, it passes it to the cloud orchestrator. The policy details is passed to the policy keeper, which enforces the policies. And for container orchestrators, and for the container, the service description, it passes it to the Kubernetes, the container orchestrators, and then they will take care of their respective details for those respective sections. MiCADO support a large variety of clouds. So far we have support for Amazon, Google, Azure, Oracle, and private clouds based on OpenStack. And the EGI Cloud Broker and Cloud Sigma are some cloud providers which are based in Europe, which is also we support through MiCADO. Now I will talk about the extension, the JQuery based extensions from MiCADO. So this extension is particularly focused on deadline constraint workload. So for example, you consider that there is a batch applications. In batch applications, usually we have these multiple job which needs to be executed within a specific deadline. So they are usually associated with the deadline. Now we don't know in advance the total exact duration for how much time these entire experiment consists of multiple jobs will be completed, because the jobs are of stochastic nature, so they may vary, their execution time may vary depend on their inputs. So now, in order to execute such applications, the problems is that what is the underlying logic, how we dynamically deploy and execute these worker containers, how we gathering monitoring statistics from these workers, so that we can formulate scaling policy, so that we can manage to execute the entire experiment within the defined deadline. So this extension, the JQuery based extension, is for this particular purposes. So what we did, we developed an additional tool called JQuery. Now, and then we integrate the JQuery in MiCADO, and the integration of JQuery and MiCADO achieve the purpose which I described on the previous slide. So if we look into JQuery, it is actually a cloud agnostic asynchronous distributed task queue, and it can be integrated with any cloud orchestrator solutions. For example, in this case, we integrated with MiCADO. It export wide range of Prometheus-based matrices about the jobs running on those specific workers. For example, how many at any point in time, how many jobs are completed, how many jobs are running, and how many time are remaining to the defined deadline. So these kind of matrices are exposed by the JQuery, which are then captured by MiCADO so that we can liaise with the deadline, the defined deadline. Now JQuery consists of two components. One is called JQuery Manager and the other is called JQuery Agent. The JQuery Manager run on a separate VM where JQuery Agent work on every workers where the jobs are executing. Now the tool JQuery, as I mentioned, it is a queuing system, so it takes the responsibility of it is that it worked as a queue where it assigns jobs to the workers, where MiCADO job is to create these workers and then at runtime look into the statuses of these jobs through the help of expose metrics by the JQuery, so that it can derive this mechanism that, okay, at any point in time, how many worker nodes will be required, so that the overall system can manage to execute within the defined deadline. Now, to understand how this works, let's look into this diagram. So as an input here, as an input to the JQuery system, we create an experiment. This is a JSON-based template. So we define the experiment in a JSON format. The experiment consists of a number of information. The most important information is that what is the deadline of the experiment, like in how long this experiment should be completed. And we also ask that the user define an estimated job duration, like for example, what is the estimated time of completion for each job? Definitely not to be exact, but it is an estimated deadline for each job. Now this experiment, this part is the JSON format which defines this file is provide like a format for this experiment. Now this JSON is submitted to the JQuery Manager, and because JQuery Manager is a queue, it submit all these jobs to MiCADO master. Now MiCADO master, there is a policy, a scaling policy defines that scaling policy determine is that at any point in time, how many workers machines will be needed, so that the jobs which are running in containers and the worker nodes, so like how many workers would be needed at any point in time, so that as a whole the system can liaise with the user defined deadline. For example, in this case, 1 hour. And this is like a pseudocode for the policy, but it could be written in a Python, just like we saw in the earlier slides. So what happened is that when this experiment submitted to MiCADO at the start, it will, based on the provided estimate time, it will calculate a number of workers and then create those workers. But at that time, it would be based on the estimations. And once some of the jobs started to execute, then MiCADO at runtime will then, based on those actual executions of job, it will calculate the new number of workers and then will dynamically create more workers, or will reduce workers which are already there if it is more than what is expected, and then it will aim to complete the entire experiment within the defined deadline. And this is how it works. Now, so that was about JQuery in integration with MiCADO for batch-based processing application. And now on the other hand, we have this second extension, which was done for the dynamic handling of containers in the cloud to edge ecosystem. So, for example, the traditional cloud to edge model is consists of such three-tier architectures where you have a cloud layers, a fog layer, and usually an edge layers, and sometimes only cloud and edge layers. So what we call, we classify that these other layers, which could be one or more than ones, we call them non-cloud layers. So now MiCADO, the MiCADO systems we described in the previous slide is only able to deploy and manage the containers in the cloud environment. But nowadays there is this growing popularity of the use of edge, the simultaneous use of cloud resources as well as edge resources. So we thought that, okay, it would be like a natural fit to extend the existing capabilities of MiCADO so that it can handle the multi-level orchestration, that is by simultaneously orchestrations within the cloud as well as on the edge nodes, or you can say on the non-cloud layer as well. Now, in order to do that, what we needed like these three additional tasks, like, for example, so in the cloud, we can dynamically create the virtual machines. But in the case of non-cloud layer, these resources, the computational resources, are physical resources, and they are already there. So now the question was that, okay, how can we let the workers join the MiCADO cluster so that they can be part of the cluster, and in that way then we can utilize them in order to deploy certain services on those nodes. And then the second challenge was that how to describe parts of the application in the same way as we are doing it for cloud-based applications using Tosca. And then the third thing was the actual task, that how to handle deployment and runtime management in the non-cloud layer. Now, in order to accomplish this, what we needed, we integrated another open source tool called KubeEdge. And with the help of these tools, what we did was like we accomplished this functionality, which take us from MiCADO, which was based only on cloud environment, to MiCADO Edge, which also include the edge environment. Now, KubeEdge in itself is an open source system for extending containerized application orchestration capability to host at edge nodes. Now, KubeEdge in itself is built on Kubernetes. So, in our MiCADO also use Kubernetes as in a container orchestrator underneath. So, it was more natural fit for our purpose, and that's why we integrated it. And also, KubeEdge is based on the same phenomena as we are working, that is the cloud agnostic behavior. So that's why we integrated KubeEdge into MiCADO system. Now, after integrating KubeEdge into MiCADO systems, what we did is that we were aiming to be able to describe the cloud to edge application in the same way as we were doing in the cloud. So the aim was that using a single uniform descriptor, we would be able to define and describe the requirement for the applications in a single descriptor, give it to MiCADO, and then MiCADO can take care of the rest. So now, and this is what we got as an extended architecture for MiCADO. So the rest of the components are exactly the same as was before. So in cloud, we running this MiCADO master, and this is the Kubernetes, which was already there. But what we have is that we have this new component called Cloud Core, which is a component provided by KubeEdge. So this is the additional component which is running on the cloud. And then on every edge workers or fog workers, we have this edge core components, which is like an agent provided by the KubeEdge component. So we dynamically configure this on every worker at the time of configuration. And now, once we configure this, then in this way, we these non-cloud workers become part of the cluster. And once they become part of the cluster, then using the same descriptors, we can then able to monitor their statuses from these worker, and as well as we also able to deploy components on top of them, the Docker containers. By the components, I mean Docker containers. Now, how this works from a description point of view. So we extended the Tosca-based description so that we can define also these edge nodes in the Tosca. For example, this one is a very simple descriptions. For example, the name of the node, and then we introduce these new Tosca types into our MiCADO ADT, like edge in this case, which will define that this is an edge node. And then in the service description, just the rest of the things are just like as was it before, and we will specify that, okay, this container will be hosted on which node. And in this case, it could be a cloud node or it could be an edge node without making any difference. And the same things will apply on the policy side. So in the policy side, we can just target any service, just like we did before. For example, in this case, now this is a service which is scheduled to be hosted on an edge node, but then we can associate any kind of scaling policies associated with it in the same way as we were doing it for the cloud-based services. For example, in this case, a container, and then we have a scaling rule for that. Like, you know, the internal details are not important at the moment, but in to summarize that, we can apply and associate any kind of scaling policies belonging to that service, which is scheduled to be run on the edge node. Now, in summary, what we can say that MiCADO system is a cloud agnostic orchestration solutions. It supports a large range of cloud providers. Its underlying architecture is very modular and pluggable architectures, where we can change a component or replace one component with another component without affecting any other systems. And that's what we did in the past. That we previously were based on Swarm, and we replaced it with Kubernetes with almost not much of effort. In terms of the functionality, it facilitates the automated application deployment in the cloud, and it has this interesting aspects of empowering the application developers to come up with any kind of customizable scaling policies. And in order to avoid lock-in, the application description is based on this standardized Tosca language. Thank you very much. And any questions, please feel free to ask. Thank you. Bye.